In this video, I want to do an overview of experiment 8. We're dealing with the composition or decomposition of potassium chlorate. Now, there's no experimental video for this lab because the experiment's pretty simple. You take this potassium chlorate, this is a balanced chemical equation describing what happens to it. It is a solid, it's a white solid, and if you heat it pretty strongly in a crucible, what happens is that you get it to decompose. Anytime you see a little triangle above or even below the reaction arrow, that means that you're heating the sample. Now, this compound, like I said, decomposes pretty easily. And what happens is that it drives off oxygen gas and it leaves behind a solid potassium chlorate. So by comparing the mass of the original sample with the mass that's left over, then we can do calculations like this. We can figure out what the percent composition of the two components are in the original compound. Now, the formulas you see here, which you'll use in the report sheet, use with the data that's in the report sheet. These are the experimental percentages. But you can also determine theoretical percentages as well, and you'll see both of those in the report sheet. The data will agree with each other pretty well. The calculations here between experimental and theoretical will agree fairly well with each other for this lab. I'm going to do a calculation, a demo calculation of this in just a minute. Briefly, what you're doing is you're looking at the total mass of the oxygen atoms based on the values from the periodic table. So these masses are coming from values on the periodic table. Like for oxygen, what you'll see on the periodic table would be something like there's an 8, which is the atomic number. That's the number of protons in the nucleus. You have the symbol oxygen. And then underneath it, depending on how it's round off or not, you'll see some number at the bottom. And this is, we call it the average atomic mass. And without going into a lot of detail here, it also can be referred to as the molar mass for a sample, like we see here. The videos for lecture 6 will explain this a lot better than I have time for here. Speaking of chapter 6, so for this semester we're using the Tro textbook 6th edition, and the percent composition is talked about in section 6.6, which we'll take a look at in just a minute. Let's go ahead and look at the report sheet and see what this data looks like for this lab. So here's our report sheet. Data is already given to you here. Now remember, the crucible is just that small ceramic dish. You know, you can model it something like that. There's a lid that goes on top of it. Pretty simple setup. It can withstand a lot of heat, and that's what's needed here. So we weigh this empty first, okay? And then we put some of our sample in it. Remember, the sample here is going to be the potassium chlorate. It's that original white salt. So if I want to know the mass of the sample, then what I need to do is just subtract these two. This is a classic kind of way to determine the mass of a sample. You know the mass of the empty container, you know the mass of the container plus a sample, and you simply subtract them. And then after heating, our new sample is going to be just the potassium chloride. Now, I've set it up here to where we're not doing multiple heatings here. It's just one heating, okay? So by the time we get to this first heating, we've driven off all of the oxygen in the form of the oxygen gas. So now if I want to know the mass of the potassium chloride, then I have to subtract these two values to get the mass of the potassium chloride. We're almost there to start doing calculations. The last thing to know is the mass of the oxygen. Well, this sample up here, that was the potassium chlorate with the oxygen. This is potassium chloride without the oxygen, and so you will subtract those two values to get the mass of the oxygen that's driven off during the reaction. And then using these 3 data points, then it's going to allow you to do these 2 calculations here for the experimental values. And these will be using the formulas that we saw on the first page of the report sheet. Let's look at how we're going to do the theoretical calculation here. And for that, I'm going to actually do an example that's taken from the textbook. So as I mentioned a few minutes ago, we're dealing with section 6.6 here. And let's just think about what it means to talk about percent composition by mass of a sample. Your classic percent calculation is, the value of what we're interested in this case, the mass of X. It could be oxygen, it could be potassium chloride, it could be chromium, like in the example that I'll do, over the total mass. So it's always, what are you interested in it? What are you interested in versus what's the total? And then times 100. In this example here, first off, just a little bit of interpretation. Just a little comment about the notation here. So chromium, right, it's just a metal from the periodic table. Its symbol is Cr. And then when it talks about a metal oxide, what that means is that there's some reaction that's taking place. Chromium reacts with oxygen from the air, and you form some kind of chromium oxide. And we pretend that we don't know the X and the Y, which I guess in this case we don't. So when it talks about metal oxide, it's this thing that it's referring to. There's some language in this in certain problems you come across, possibly in the lab, pre and post lab questions. So I just want you to be aware of how to handle this kind of calculation. The example that's shown in the book is the mass percent of chromium. Okay, so there's the mass of chromium. Well, the other thing you often have to do is also do the mass percent of oxygen. So just notice, like in this example, if I have the total mass of the product here and then the mass of the chromium here, then I would just subtract these two to get the mass of the oxygen. I don't know if I have enough room here. 523 grams minus 0.358 grams. That's the mass of the oxygen over the total mass times 100. Now, I'm not going to do this calculation. I actually want to talk about the distinction between experimental versus theoretical. Okay, that's what I want to do here. So when it's raw data from the lab, this would be the experimental value. Now, if I want to do the theoretical value for this example, well, one thing I need to know is the molecular formula, which in this case, I do know. It's actually, this is chromium 3 oxide. So if I want the theoretical mass, percent mass of chromium, well, what that's going to look like is, and I'm using the formula that's kind of set up in the lab report. And the basic breakdown here is how many chromiums are present compared to the entire set of atoms in my molecule. Well, I see from the molecular formula I have 2 chromiums. Okay? Now, if I look on the periodic table, the molar mass for chromium is 52.00. The unit on this one really doesn't matter. You could think of it as AMU, i.e. atomic mass units, or since I'm using the language molar mass, then I'm going to use grams per mole. This unit is discussed in chapter 6. Now the total mass here, if I want to do the molar mass of this chromium oxide, well, what I have to do is I have to take inventory of the entire set of atoms that I have here. I have 2 chromiums, all right, so each chromium weighs 52.00. I'm going to drop the units just for simplicity here. Oxygen, well, I can see there's 3 atoms there. Each oxygen weighs 16.00. Practically what I always do is I round off to two decimal places from the data on the periodic table. So if I multiply these out and then add them together, what I get is I get the molar mass of this compound, which is coming in at 151.99 grams per mole. So that's what's going to go on my bottom part of the denominator in my formula here, if you will. And then times 100%. Again, what am I interested in? I'm interested in the percent mass of chromium. How much chromium do I have in there? Well, I got this mass of chromium compared to the total mass of the entire sample. The general form, whether it's theoretical or experimental, it's still the same. What you're interested in divided by the total. And then if I do the math here, I come in at 68.43%. And there's always going to be a little bit difference between the experimental and the theoretical. That's just how science works. Okay. The fact that these two agree so well, that's how I know that this chromium oxide is actually chromium 3 oxide, this formula here, okay? This is the kind of setup that you're then going to use for the theoretical values here. So again, these values are going to be taken from the periodic table, basically. There's 2 more data points, 2 more calculations you need to do for the report sheet, the percent error for the oxygen and the potassium chloride. Depending on the values here, and there's a couple variations in this formula, but for this lab, one of these will be negative, one will be positive. Okay, I can't remember which is which. The formula for the percent error is actually on that first page. Let's take a look at it. And it's right here. And then notice the big difference is between the experimental value and the theoretical value. So the difference between those 2 values you calculate divided by the theoretical value times 100. And notice you're performing this subtraction function first before doing the division function. I can tell you for this particular lab, it's pretty small. The data you have here are pretty good, okay? And I think that's a decent overview for this lab. Thanks.